Hello student, we are studying our third module, that is the photovoltaic systems. In that we have covered the introductory part, how the solar cell works, and the how the solar cell acts as a constant current source. Also we have discussed the IV characteristics of the solar cell and different parameters which are help us to study the solar cell, that is the field factor, efficiency of the solar cell, open circuit voltage and short circuit current. All these parameters which have been discussed in our last videos or previous video. So these parameters which are very important for the solar cell. Now in this video we start with the limitation to the photovoltaic efficiency. As we discussed in our previous video, the efficiency is the ratio of the maximum power which can be obtained from the solar cell to the input power to the solar cell, but it has some limitations. That means as we consider the structure of the solar cell, there is a different types of the transparent cover, and the construction of the solar cell has some defects in the construction of the solar cell, that means in the material. Nowadays the solar cell is constructed with the help of different techniques, that means the thin film techniques. So these thin film techniques which help us to reduce the different types of losses, but still there is some losses in the solar cell and which affects the efficiency of the solar cell. So let's see the limitation to the photovoltaic efficiency. Photovoltaic cells are limited in efficiency by many losses. Some of these are avoidable, but others are intrinsic to the system. That means some losses which we can avoid, that means they are avoidable for the different arrangement because of the different arrangements which are available, but some are the intrinsic, that means they cannot be avoided with the help of any different parameters or any device or any requirement to the system. So these all are the intrinsic parameter and which affects the efficiency of the solar cell, that means it affects the photovoltaic efficiency. So first parameter is the first loss which affect on the photovoltaic efficiency, which is the top surface contact obstruction, and which is nearly about 3% loss, which introduce about nearly 3% loss to the photovoltaic efficiency. The electric current leaves at the top surface by a wave of metal contacts arranged to reduce series resistance losses in the surface. That means as we discussed about the construction of the solar cell or diagram of the solar cell, in that there is a metal strip on the top surface. For the this metal strip helps to leave the electric current at the top surface, and so this arranged also to reduce the series resistance losses in the surface. That means if we have the value of series resistance is large, then we are able to obtain the less current, and which is not good for the solar cell. So if we have the large shunt resistance, that means the parallel resistance, then the solar cell is good, but if this series resistance is large, then the solar cell is not good. So to reduce this series resistance, there is a metal contact on the top surface and which helps to leave the electric current. This loss is not always accounted for in a efficiency calculation. That means there is a efficiency calculation for the solar cell. There is a derivation for the efficiency. From that we consider different parameters which affects the solar cell, and from that we introduce all that parameter in the solar cell efficiency, and we get the equation for the solar cell efficiency. But the loss due to top surface contact obstruction is negligible. That means this loss is not always taken into account for the solar cell efficiency calculation. So this is the first factor which affect the photovoltaic efficiency. The second factor is the reflection at the top surface, and this introduces the loss near about 1%. We know that there is a large amount of reflection in the solar cell due to different transparent covers which are used in the solar cell. Without special precaution, the reflectance from the semiconductor is high, which is nearly 40% of the incident solar radiation. If we take some precautions, then the loss is very small, but without any precaution the loss is very high, that is nearly 40%, and which is not good for the good solar cell, or this is not good for the to obtain the this is not good for to obtain the better efficiency. So without any special precaution the loss is very high. If we take some precaution, the loss can be reduced. So the maximum solar radiation which can be reflected from the glass surface. So if we take proper precaution for that, then we can able to obtain the good efficiency for the solar cell. The reflection loss is due to transparent cover and due to edges of the solar cell. Generally in a solar cell, the reflection loss occurs due to transparent cover which are at the top surface, and also for the from the edges of the solar cell. From the edges, due to there is some deficiency or some problems in the construction of the solar cell material, that is the semiconductor material. Due to that there is some losses due to defect in the construction of the semiconductor material. This loss can be minimized by using thin film technology of the solar cell. Before that, the edge reflection is arises due to improper concentration of doping of solar cell. That means the losses from reflection losses from the edge of the solar cell can be minimized with the help of different techniques, and this occur due to improper concentration of doping of the solar cell. That means the material which is used in the solar cell, which is the semiconductor material, and which can be formed with the help of doping. So if we introduced improper concentration of the doped material, then there is a problem, that is there is a reflection from the edge of the solar cell, and which is not good for the efficiency because it introduces some solar cell radiation losses, and so we get the less current or less amount of heat from the solar radiation due to reflection. So this introduces the loss to the solar efficiency. This loss can be minimized by using thin film technology of the solar cell. With the help of thin film technology, we are able to obtain the uniform thin film. That means we are able to avoid the different defects or improper concentration of the doping material. If we use the thin film technology for the solar cell, then there is a formation of uniform thin film, that is a proper thin film concentration. So this loss can be minimized with the help of that techniques. Next loss, the incident photon. Next lost is the when the energy of the photon is less than the photon energy. So this loss is the incident photon of the quantum energy, that is h nu is less than Eg, cannot be contribute to the photovoltaic current generation. This is the third parameter. That means the energy of the photon is less as compared to the band gap of that particular semiconductor. We know that the sunlight consists of different photons, and the photons has the energy, and which is the h nu, and in the semiconductor material there is a band gap, that is the gap between the valence band and the conduction band, that is the energy gap, and which is known as the band gap. If we have the photons which have energy less than that band gap, so this photon cannot be contribute to the photovoltaic current generation. That means this photon cannot be absorbed by that electron or by that electron, so that there is no generation of the current. So these photons contribute to the heat generation, and due to heat generation there is a loss of that particular heat, and this heat cannot be useful for the solar cell. So when we have the energy of the photon is less than the band gap of that material, these photons are not useful for the, or this photon cannot be contribute to the solar cell efficiency. So this introduces the loss. If this energy is absorbed, it causes heating with a temperature rise that lowers power production still further. If this energy is absorbed, that means the photon which has a energy less than the band gap, if this energy is absorbed, it causes heating, unwanted heating, and there is an increase in the temperature of that solar cell. So there is obviously the decrease in the power of the solar cell. This loss can be maintained by proper concentration of the doping material. This loss can be also maintained with the help of proper concentration of the doping material, because if the doping is a proper, then there is a proper band gap, so the photon gets absorbed by that particular electron, so that it can excite from the valence band to conduction band. That means the photons gets absorbed easily, and all these photons are utilized for the current generation, so that we are able to obtain the maximum efficiency for that solar cell. Next parameter is the excess photon energy, and which introduces loss near about 33%. There is a possibility the energy of the photon is also greater than the band gap of that particular semiconductor material. If this happen, the excess energy active photons also appears as a heat. That means if the photon has a energy larger than the band gap of that particular semiconductor, these photons also cannot be absorbed by that electron, so it also contribute to the heat production in the solar cell, and which is not good for the efficiency of the solar cell, or the for the good solar cell. So this introduces the losses near about 33%. Next parameter is the quantum efficiency, and the loss due to quantum efficiency is nearly about 0.4%. When the incident solar radiation get absorbed by the solar cell, the maximum amount of electron hole pairs are generated. As we discussed in the working principle of the solar cell, when we incident the sunlight on the solar cell, there is sunlight consists of the different photons, and if the photons have energy is equal to the band gap of that particular semiconductor material, then this photon gets absorbed by that semiconductor material, and there is the formation of the electron hole pair. Thus the design of the solar cell has to ensure that the material is thick enough for at least 95% absorption. For that absorption process, that means the photon absorption process, it is necessary, or it should be necessary, that the material should be thick enough for at least 95% for the absorption. That means the material is constructed in such way that, so that it can absorb maximum amount of photons from the sunlight. That means the 95% absorption. So we are able to obtain the maximum current from the solar cell. Reflecting layers at the rear of the solar cell can return transmitted radiation for a second pass. That means we have different transferring glass plate which covers the upper part of the solar cell, and which help us to transmit or to reflect the reflected radiation, and again this reflected radiation contribute to the current generation. In this way we are able to improve the efficiency of the solar cell by taking different precautions. Now the next parameter is the collection efficiency loss. Due to collection efficiency loss, the loss is near about 1 to 2%. That means this collection efficiency introduces loss nearly about 1 to 2%. It may be applied to include a losses due to photon energy less than the band gap, or excess photon energy are usually as here to electrical collection of charges after carrier generation. As we discussed, there is a photons which have energy maximum than the band gap of that semiconductor, or less than band gap of that semiconductor. There is a two possibility, but after that again there is a probability phenomena. That means after generation of the electron hole pair, that means if we consider the sunlight, then the sunlight get incident on the solar cell. After the incident After that, there is the absorption of the photons which have energy equal to the band gap of that semiconductor, and there is a creation of electron hole pair. But after that, the collection of the electron and hole, if this process is not taken place in a proper way, that means maximum number of electrons hole pair should be collected. If the collection efficiency is low, then obviously the solar efficiency is also low. So the collection efficiency is very important parameter for the solar cell. For the good solar cell, the collection efficiency is good. The collection efficiency is therefore defined as the proportion of radiation generated electron hole pairs that produce current in the external circuit. That means the current which produced in the external circuit, which depends on the electron hole pair collection. That means how much electron hole pairs are collected, this decides the current in the external circuit. If electron hole pair generation collection is a maximum, then the current in the external circuit is also maximum. So this parameter plays very important role in the efficiency of the solar cell. Next parameter is the voltage factor, and this introduces losses near about 20%. Each absorbed photon produces electron hole pairs with an electrical potential difference of Eg divided by E, where Eg is the band gap and E is the charge on the particular carrier. That means the electron or hole, but the charge on the both is the same. On the electron there is a negative charge, and on the proton or the electron or hole, the charges are in opposite in polarity, but the magnitude is the same. So the E is same for both electron and holes. So the Eg upon E, this is the an electric potential difference. That means each absorbed photon produces electron hole with an electric potential difference of Eg by E. That means when the solar radiation is installed on the solar cell, there is absorption of the photons and this produces electron hole pair. So this electron hole pair creates a or constitute a electric field or potential difference, and which is the Eg by E. That is the ratio of the band gap of band gap energy, that is Eg to the charge. When producing a current on a load, the moment of carriers under forward bias produces heat as a resistive internal impedance heating. So there is a decrease in the voltage. This may be included as a voltage factor. We know that when producing current on the load, that means there is a load, that means the external circuit. When there is a current in the external circuit, the moment of carriers under forward bias produce heat as a resistive internal impedance. That means when there is a moment of the charge carrier, there is a production of the heat, and this heat contributes to the internal resistance of that system or that circuit. So due to increase in the internal resistance, there is a decrease in the voltage. So this introduces the loss in the efficiency, and this loss is known as this may be included as the voltage factor loss. That means due to decrease in the voltage, there is a decrease in the efficiency, and all this happens due to the increase in the internal resistance due to heating effect in the solar cell. So this is the voltage factor. Next parameter is the shunt resistance, and which introduces about loss, which is the 20%. The shunt resistance is caused by the structural defects across and at the edge of the solar cell. That means, as we discussed, there is a structural defects in the construction of the solar cell material, that is the semiconductor material, and at the edge of the solar cell, and the edge losses is also occurs due to the improper concentration of the solar cell or improper concentration of the doping material within the solar cell. So this loss can be minimized with the help of using different techniques, that means the thin film techniques. So with the help of that techniques, we are able to obtain the uniform material, and so it has a less structural defects, and due to that there is a less in the losses from the solar cell, and so that the shunt resistance is high for the good solar cell. If the structural defects in the solar cell, then the shunt resistance is very low, but this is not for the good solar cell. So for the good solar cell, the shunt resistance should be very high. Second point is the present technology has reduces this to the negligible effects. So shunt resistance may be considered infinite to single crystal silicon solar cell. The single silicon crystal solar cell is the solar cell which has a good efficiency compared to the other solar cells, and which has the infinite shunt resistance. That means it is a good solar cell and which is constructed with the help of present technology. That means the thin film technology for their construction. So the single crystal silicon solar cell gives better efficiency as compared to other types of the solar cell. This may not be in a polycrystalline solar cell. That means generally there are two types of the solar cell, that is a single crystalline solar cell and the polycrystalline solar cell. In a single crystalline solar cell, the efficiency is better. That is if we consider the example of the silicon solar cell, the efficiency is better. But in the polycrystalline solar cell, there is one or more, two or more crystals. That means the formation of the material with the help of different crystals. So there is a material, so that one crystal and first crystal and second crystal is separated by the grain boundary, and this grain boundary introduces the decrease in the current. So to overcome that grain boundaries, so there is a decrease in the current. So this is not good in the polycrystalline solar cell. So due to that formation of the grain boundary, the efficiency of the polycrystalline solar cell is less as compared to the single crystalline solar cell. So the efficiency of the silicon single crystal solar cell is better or good than the other solar cell. So these all are the different parameters which affects the efficiency of the solar cell or photovoltaic efficiency. But this can be minimized, not completely but in a less amount, with the help of different techniques, that is the thin film techniques for the construction of the solar cell, and by taking particular precaution for that losses, so we are able to improve the efficiency of the solar cell. So this is all about the efficiency of the limitation to the efficiency of the solar cell or photovoltaic efficiency. Now in our next video we will start with the new point. So we will continue with that.